Have you ever really thought about how a simple idea gets turned into one of those impossibly complex microchips that, well, powers pretty much everything? Today, we are going to pull back that curtain and trace the entire journey, all the way from a blueprint to the finished product.
Yeah, that's the big question, right? How do you go from a bright idea to a chip packed with literally billions of transistors? It might seem like magic, but it's actually one of the most incredibly structured engineering processes out there. We're going to break down the whole thing, the application-specific integrated circuit, or ASIC, design flow, from the very beginning to the very end.
So here's the master plan. The whole process is really split into two giant phases. First, you've got the front end. That's all about the abstract idea, defining what the chip is supposed to do. It's the blueprint. Then you have the back end, and that's where we take that blueprint and figure out how to actually turn it into a physical object that you can manufacture.
Okay, let's start at the very beginning. In the world of pure logic and function, welcome to the front end. This is where the architects and designers get to dream up what this chip is going to be.
It all kicks off with a specification. Think of it as a detailed document that spells out exactly what the chip needs to accomplish, sometimes written in a high-level language like C. From there, designers have to manually translate that behavior into a special kind of code called RTL. And this is so important. At every single step, they verify, running simulation after simulation to make absolutely sure the logic is perfect.
So, what is this RTL thing anyway? You got to think of it as the architectural language for chips. Engineers use languages like Verilog or VHDL, but here's the key. They're not writing software. They are literally describing the physical hardware in code. They're defining how signals flow between tiny storage elements called registers, essentially drawing the chip's functional blueprint.
And that brings us to what is often the most time-consuming part of the whole front-end process. You've got this beautiful blueprint written in code. It looks great, but before you even think about building a single thing, you have to be 100% sure it actually works.
This is logic verification, and it's a huge deal. It can easily eat up more than half of the entire project's time. Engineers build these super complex virtual worlds just to throw every possible scenario at the design. It's kind of like running a million digital fire drills. Why? Because finding a bug here is just a few keystrokes to fix. Finding that same bug after the chip is made, that can cost you millions.
All right, so once the blueprint is finally verified and we know it's correct, we get to this amazing moment. It's called synthesis, and it's like this magical bridge that connects the abstract world of code to the very real, very concrete world of physical electronics.
And as you can see from this flow, synthesis is not just flipping a switch. It's a really complex automated process. You've got these incredibly sophisticated tools that take our verified RTL code as the input, and they start translating it into a list of actual physical logic gates. You know, the fundamental building blocks of any digital circuit.
Now, this synthesis tool is just unbelievably smart. It optimizes the logic, trying to find the perfect balance between speed, how much space the chip takes up, and how much power it uses. Then, it does something called library mapping, where it swaps out generic logic for very specific pre-designed components called standard cells from the manufacturer's toolbox. And finally, it uses something called formal verification to mathematically prove that this new gate-level design is a perfect match for the original RTL blueprint.
And what comes out at the end of this whole synthesis process? The netlist. This is it. This is the definitive recipe for our chip. It's basically a giant text file that lists out every single logic gate and every single wire or net that connects them all together. With the netlist in hand, we are officially ready to say goodbye to the front end.
We are now entering the back end. You know, if the front end was like designing a blueprint, the back end is basically urban planning and construction, but for a microscopic, super dense city. This is where things get physical.
The very first step is floor planning, and it's exactly like zoning a city. Engineers decide where all the major districts are going to go. You place the big pre-designed blocks like memory first. Then you set aside areas for the millions of tiny standard cells, which get organized into these nice, neat rows. Getting this initial layout right is absolutely critical for the chip's performance.
So after the floor plan, we hit two massive stages, placement and routing. Placement is pretty much what it sounds like. You take every single gate from our netlist, every building in our city, and you give it a precise XY coordinate. Once every single thing has a home, routing begins. And that is the mind-boggling task of laying down all the metal wires that connect every single one of those buildings.
Now, this whole place and route flow is this incredibly complex, automated dance. And as you can see, it's not a straight line. The tools place the components, they route the wires, and then they immediately run checks. Is the design fast enough? If the answer is no, it gets kicked back into this loop of tweaking and rechecking until it finally hits the target.
And routing isn't just about connecting logic either. It also involves creating these huge tree-like networks for power and ground to feed every single component. And maybe most importantly, it includes the clock tree, this special network that delivers the chip's master heartbeat, making sure every single part of this huge city acts in perfect sync.
So the chip city is built. The roads are paved, but now it has to survive a final gauntlet of stress tests. These are the physical verification steps that make sure the design not only works, but that it can actually be manufactured and will be reliable out in the real world.
But there's a problem. See, back in the perfect abstract world of the front end, a wire is just a perfect connection. But in the real world, physical wires have resistance. They have properties that create delays, basically electrical traffic jams. And those traffic jams can break the entire design. So, how do we account for that? Well, we use a process called parasitic extraction. A tool goes through the final physical layout and calculates all those unintended or parasitic electrical properties of the wires themselves. This gives us a super realistic model of how signals are actually going to behave when this thing is made of real silicon.
And now we take all this super accurate parasitic data and we feed it into the final exam, static timing analysis, or STA. This tool checks every single signal path in the entire chip exhaustively to make sure every calculation can finish within a single tick of the clock. Any path that's too slow gets flagged as a timing violation.
And what happens if it fails? We follow that no path. A failure here isn't a disaster, it's just a normal part of the process. The design goes back for more tweaks, moving components, rerouting wires, and the whole analysis loop runs again. This fix and verify cycle just keeps going until every last one of the millions of paths meets its goal. When every check is finally passed, the design is taped out. This final, verified database gets sent off to the CMOS fabrication plant, the fab, which is this multi-billion-dollar facility where over hundreds of steps, our digital blueprint will finally become a physical reality. So when you look at the whole thing, you see it's this constant battle between two worlds, right? You have the clean, perfect logic of the front end versus the messy, unforgiving physics of the back end. It kind of leaves you with one last question. What's the bigger challenge? Coming up with a perfect idea or making sure that idea can actually survive contact with the real world?